In this video, we will dive into tokenizers with the help of Andrej Karpathy's latest video of explaining the tokenizers behind GPT-2. Let's dive in. Imagine tokenization as the art of breaking down language into its smallest, meaningful components, tokens. This can be words, characters, or even parts of words. They are the essential elements that sophisticated models such as the transformer neural network use to understand and generate language. The essence of tokenization is the key process by which we transform raw text into a format that language models can understand. Think of it as breaking down a sentence into individual building blocks. These blocks are called tokens. Tokens can represent whole words, subwords like prefixes or suffixes, or even individual characters. Language models work with numerical representations, not raw text. Tokenization provides the bridge, translating human language into a structured format for computation. The way we tokenize text significantly influences how the model learns to process and understand language patterns. Vocabulary is the model's dictionary. Each language model has a vocabulary, a comprehensive list of all the tokens it knows. When a model encounters a word outside its vocabulary, it might need extra help to understand the context or generate meaningful responses. Context size is the window of attention. Context size determines how many surrounding tokens a language model considers when focusing on a specific word or phrase. This attention window allows the model to understand how tokens relate to each other, which is crucial for grasping the nuances of language. There are some challenges of tokenization, like spelling and variations. How does the model handle typos or unusual word forms? Robust tokenization helps models address misspellings and variations for better understanding. Different languages have distinct word structure and grammar rules. Adaptable tokenization is needed to support language models that work with multiple languages seamlessly. Teaching a model to perform basic calculations requires tokenizing numbers and math symbols in a way it can interpret. The choice of tokenization directly influences model's performance. Fine-tuning how we tokenize text can lead to improved accuracy, like models can grasp context better, leading to more meaningful responses. And computational efficiency, like smarter tokenization can reduce model size and processing time. And fairness and bias, like careful tokenization helps reduce the risk of language models perpetuating stereotypes or unfair associations. Let's remember, tokenization isn't just a technical detail, it's the gateway to models' understanding of the language. By perfecting this process, we can create language models that are more versatile, accurate, and reliable across a wide range of natural language tasks. Moving to our second slide, we delve into basics of character-level tokenization and how it's implemented using Python. The building blocks of text. Character-level tokenization treats each letter, numbers, punctuation mark, and even spaces as individual tokens. This approach lets language models learn the fundamental structure of language from the ground up. Unlike word-level models, the vocabulary here is simple. It includes all the characters present in your dataset. There is no need for complex splitting or stemming techniques. We assign a unique numerical ID to each character in our vocabulary. This establishes a code that model can use to translate text into machine-readable sequences. The tokenization flow, and here's how it works. First, text input. We feed our model a piece of text. Then, character breakdown. Model splits the text into individual characters. Then, token lookup. It replaces each character with its corresponding numerical ID from the mapping. Then, token sequence. The result is a sequence of numbers that represents the original text to make it ready for the model to process. Let's talk about advantages of character-level tokenization. First, no out-of-vocabulary issues. Any text can be handled, even with unseen word or misspellings. It handles morphology. Models can learn word structure, like prefixes, suffixes, etc., and smaller vocabularies, reduces model size and can improve computational efficiency. Note that character-level models often lead to longer sequences, so they can be computationally slower to train than word or subword-based models. As we progress to our third slide, we explore the realm of advanced tokenization techniques, starting with Byte Pair Encoding or BPE. BPE is a method that iteratively merges the most frequent pairs of tokens in our text data. This process is akin to a compression algorithm, where common pairs are replaced with single new tokens, effectively reducing the size of our text representation. The evolution of BPE has given rise to SentencePiece, a more sophisticated tokenization method that introduces subword units. Unlike BPE, which relies on predefined vocabulary, SentencePiece operates directly on raw text, allowing it to preserve more information and adapt to a wider range of languages and vocabularies. Let's delve into key concepts of SentencePiece. It's designed to be language neutral, meaning it can tokenize text in any language without bias. It also uses a statistical model to determine the most effective subword units for tokenization, ensuring that the vocabulary is optimized for the text at hand. To support these ideas, let's look at the Python code example that demonstrates a basic BPE implementation. This code snippet illustrates how we can start with an initial vocabulary and iteratively merge the most frequent pairs of tokens to build a new compressed vocabulary. Now, as we transition from BPE to SentencePiece, we see several enhancements. SentencePiece can handle a larger vocabulary and provides a better representation of text data, which is crucial for effective learning in language models. It's these advancements that make SentencePiece is a powerful tool in the NLP toolkit. By understanding BPE and SentencePiece, we gain insight into how tokenization has evolved to meet the demands of modern language processing. These techniques are not just about reducing text size. They are about capturing the essence of language in a way that's both efficient and effective for our models. Slide 4 takes us into the intricate world of GPT-2 and its use of byte-level encoding. GPT-2, a state-of-the-art language model, employs a tokenization approach that goes beyond simple character-level encoding. By using byte-level encoding, GPT-2 can effectively manage a vast array of characters and symbols, making it incredibly versatile across different languages and text formats. Byte-level advantage. GPT-2 breaks free from the limitations of character-level encoding. Byte-level encoding allows it to represent a wider range of characters and symbols efficiently, crucial for handling diverse text found in the real world. Let's explain byte pair encoding. It starts simple. BP begins with individual bytes, often representing characters. Then iterative merging. The algorithm identifies frequently occurring byte sequences and merges them into new tokens. Then balancing vocabulary. This process strikes a balance between managing uncommon words and maintaining a reasonably sized vocabulary. BP constructs GPT-2's vocabulary dynamically from the training data. This means adaptability. The model can learn patterns from real-world text, including new words, slang, and technical terms. The vocabulary isn't restricted by a predefined list. BP can still represent less frequent words as combination of common subword tokens. Vocabulary size is kept manageable, improving model storage and computational speed. Beyond whole words, SentencePiece tokenizes based on subwords like prefixes, suffixes, etc., capturing linguistic patterns for better understanding. It has multilingual advantage. This flexibility makes it ideal for languages with complex word structures or for translation tasks where consistent tokenization across language is key. By using BP and SentencePiece, GPT-2-style models achieve robustness. They handle messy real-world text with typos, unusual words, and diverse scripts more gracefully, and improve accuracy. They can grasp context better due to more nuanced tokenization approach. Slide 5 brings us to critical discussion of the impact of tokenization on language model performance. The language model's foundation. The way we tokenize text isn't merely a pre-processing step. It lays the groundwork for how the model understands and generates language. The choice of tokens directly shapes the model's learning process and influences the quality of its output. Then context size. Think of context size as the model's field of vision. It determines how many surrounding words the model considers when analyzing a specific word or phrase. Too narrow a context and the model misses the bigger picture. Too wide and it loses focus on important details. Finding the optimal context size is crucial for the model to grasp complex relationships within the text and maintain consistency in its output. Vocabulary and context. A limited vocabulary restricts the model's ability to process a diversity of real-world language. A rich vocabulary allows for more nuanced representations of words and their meanings. Contextual awareness. The context window lets the model understand the relationship between tokens. This is crucial for disambiguating homonyms like bank as financial institutions versus a river's edge, and handling figurative language. Challenges and considerations. Handling long sentences. Models can struggle to maintain coherence and focus over very long stretches of text. Tokenization techniques must be able to gracefully handle varying sentence lengths to help the model process the information effectively. The risk of misinterpretation. Purely defined tokens or tokens that don't align with linguistic patterns can introduce errors. This can lead to hallucinations and factually incorrect responses from the model. The importance of iterative design. Tokenization isn't one and done process. We need to experiment, analyze model performance, and continually refine our tokenization to address weaknesses. And impact. Why tokenization matters. Accuracy and coherence. Well-designed tokenization underpins the model's ability to understand language accurately and generate text that makes sense. Careful tokenization can help mitigate the tendency of models to perpetuate stereotypes found in training data. Efficient tokenization allows model to better handle new words, slangs, or text from specialized domains. Tokenization has a ripple effect throughout the entire language model process. By mastering this fundamental step, we can create models that exhibit. As we conclude our journey through the world of tokenization, let's crystallize the best practices that will lead us to optimal model training and inference. Tokenization is not just a technical step. It's an art that requires a thoughtful approach to ensure that our language models reach their full potential. Start with a well-defined vocabulary that strikes a balance between richness and efficiency. Determine the optimal context window for your model, the lens through which it views language. Ensure each token captures linguistic patterns, not just surface-level text. Strive for tokens that aid understanding, particularly in complex or ambiguous passages. Calibrate tokenization for the most effective use of model's attention mechanism. Aim to minimize attention overhead while maximizing its ability to extract contextual relationships. Continuously evaluate the interplay of vocabulary, context size, and model performance. Avoid overfitting to one task. Keep adaptability across different use cases in mind. Anticipate tokenization challenges early. Design for multilingual support, numerical reasoning, and handling specific data formats. Robust tokenization empowers successful model training and accurate inference. Invest in this foundation. Tokenization is far more than a technical detail. Let's commit to experimentation. Explore different techniques, word, subword, BPE, to find the best fit for each task. Evaluation. Critically analyze how tokenization impacts model output. Tokenization is an evolving field. Stay updated on new techniques and best practices. By mastering tokenization, we can unlock the true potential of language models, pushing the boundaries of what's possible in the realm of natural language processing. If you enjoyed this content, please remember to like and subscribe to the channel.